Now that we're familiar with rules of inference, let's look at the various methods of proof that rely on these rules of inference. For example, let's prove that there exists an even integer that is the sum of two primes. We can write this as there exists a k such that p of k, where the domain of k is the set of even integers and p of k is the predicate k is the sum of two primes. Okay, now in order to show there exists a k such that p of k, we just need to find one even integer that is the sum of two primes. Okay, in other words, we just need to show p of c for some c. Okay, for some c in the set of even integers. Okay, we're using the rule of inference called existential generalization. And remember that rule goes like this. P of c for some c and therefore there exists a k such that p of k. Okay, note that 8 is equal to 3 plus 5, where 8 is even, and 3 and 5 are primes. Okay, thus we found one even integer that is the sum of two primes. Thus, by existential generalization, there exists an even integer that is the sum of two primes. We can also disprove a statement by providing a counterexample. For example, let's disprove the following statement. For all integers n, if n squared equals to 4, then n equals to 2. We can write this as for all n, if n squared equals to 4, then n equals to 2. That is, for all n, p of n entails q of n, where the domain of n is the set of all integers and p of n is the predicate n squared equals to 4, and q of n is the predicate n equals to 2. Okay, note that not for all n, p of n entails q of n, that's equivalent to there exists an n such that not this, and that's equivalent to there exists an n such that p of n and not q of n. So to show that this statement here is false, we can show this statement here. There exists an n such that p of n and not q of n. In other words, we can show p of c and not q of c for some c. For some c in the set of integers. Okay, here we're using existential generalization. So if we can show this, then we'll be showing this. And that's equivalent to the negation of this universal statement. Okay. Note that negative 2 squared is 4, and negative 2 is not equal to 2. Okay, thus we found one integer whose square is 4, and that is not equal to 2. By existential generalization, there exists an integer whose square is 4, and that is not equal to 2. Okay, minus 2 is a counterexample. It's a counterexample to the universal statement, which says for all integers n, if n squared equals 4, then n equals 2. Okay, so minus 2 is a counterexample to this statement. Okay, so we used a counterexample to disprove the universal statement.